All right, good evening. So why don't we get started today? I'll take anyone's questions. Just go ahead and type them into the chat bar there. Where can we get started? Number 7 on the review. Okay, let's see. All right, so let's take a look at number 7 on the review. All right, so we have we have something that looks like this. Okay, and then we're asked, we have two curves, so y is equal to cosine of 2x, and then y is equal to sine of x. Okay, so this one is y is equal to sine of x, and then that one here is going to be y is equal to cosine of 2x. Okay, and then we're asked to find the shaded area. All right, and then we're told that this is 2 sine squared x. That will be helpful. Okay. All right. Okay, so what I need to find out first, so what I can do here is to find the area in between the two curves, we're going to have to take the integral of f of x minus g of x dx. Okay, but so it's a matter of the top one minus the bottom one. The problem here is that they switch here, but that's okay, right? So we need to find out what are these points right there. Okay, so let's take a look at, well, first we have to solve, again, when both of these are equal to each other, right? When this equation is equal to that equation. So we'll look at all right, so we need to solve this equation. And here, I'm going to put to use that that identity that was given to me. Okay, so I'm going to plug in minus 2 sine squared x equal to sine of x. All right, and then here I'm gonna, looks like I have a quadratic form. All right, so I'm gonna move everything over to the other side. All right, so it'll look something like this, and now I'm going to factor. It looks like I can factor it like this, right? Let me just do a quick check. 2 sine squared of x, negative 2 sine of x plus sine of x gives me a negative. And then 1 times a negative 1 gives me that negative 1 there. Okay, so now I've set this, let me set this equal to 0. So now we have, when is sine of x sine of x is equal to 1, and then 2 sine of x is equal to negative 1. Excuse me. Yeah. Okay, so here, sorry, I got a quick mistake here. I made this is still plus, so I have to change a couple things here. Let's see here. So I move this over here, minus 1, that's still plus, so that means that this should be minus, and that one should be plus. Okay, sorry about that. I missed a sign here. That should be a positive sine x, and this should be positive, and that should be negative. So the factored form should look something like this. Okay, so we have 2 sine of x minus 1 sine x plus 1 equals to 0. Okay, so that would be the factored form of this. Okay, so again, I made a bit of I was rushing through here and I kind of messed that sign up, but now we should have the correct factored form, right? 2 sine squared plus 2 sine x minus sine x gives me back that positive sine of x. And then that last one is still minus 1. Okay, so now I got to solve this. All right, so solving this, here we have twice sine x minus 1 equals to 0. Or sine of x is equal to, or sine of x plus 1 is equal to 0. All right. Okay, so looking at here, looking at this one here, sine x plus 1 equals to 0, that means sine of x is equal to negative 1. And that happens when, well, the first time it happens is when x is equal to 3 pi over 2. All right, now if you look at the graph that was given to me, and I don't have it, well, here, let's take a look at what I have here. Okay, so what we see here is 3 pi over 2 is somewhere out here. So I'm not going to use, that one is not going to be my one of the points that I'm looking for, right? This is pi, 3 pi over 2 is somewhere out here. So that solution is not going to give me those 2 points there. All right, so what is going to give me those 2 points is looking back at the other part of my equation. I have 2 sine of x is equal to 1, or in other words, sine of x is equal to 1/2. Okay, now sine of x is equal to 1/2. It's positive in the first and the second quadrant. And the first time that happens is when x is pi over 6. And then the next time it happens is when x is 5 pi over 6, right? In quadrants 1 and 2. Okay? All right, now as it turns out, those are going to give me the points right here, right? That'll be pi over 6. The next time it happens, it'll be at 5 pi over 6. Okay? All right, which means that now I have the points where I can now have my limits of integration. Okay, so here, the first integral, right? I'm going to refer back to my, what would you like me to explain, Grissom, right? Well, that's from our unit circle, right? If I want to solve that equation, sine is positive in quadrant 1 and quadrant 2. All right, so those are just my reference angles when I'm trying to solve something like this. This I refer back to my unit circle. Okay, so that's where I got these values. All right. And it's positive. And again, right, it's it's a periodic function, but if I look at my picture, I'm really only worried about the first positive first terms, right? Pi over 6 and then 5 pi over 6. It'll come back again later to kind of meet, but really I only care about those, okay? So that the first time that it happens in the positive x. Okay. All right. So now what I have here is I'm going to have my first integral is going to be the top curve, which is going to be cosine of 2x. And I'm going to subtract the bottom curve, which is sine of x dx. Okay, and from here, it'll go from 0. Again, right, they give us a very definite starting point at 0. And then the first intersection point would be pi over 6. Okay. Oops. Okay. And then from there, the next one, they'll flip. So from pi over 6 to 5 pi over 6, we'll get sine of x minus cosine of 2x dx. Okay, and then from here we integrate. Be careful with this one, this cosine of 2x. All right, remember when you it's a chain rule here, so when we work backwards, because Marlon, it's the reason they flip is because the reason we found those points was if we look at our graph. Right, so when we have our graph, what we see is, remember, it's top minus bottom. All right, here, the top is y is equal to cosine of 2x, and the bottom is sine of x. All right, so here we have this condition, right, top minus bottom. All right, good. And then after that, it flips, right, which is why we had to go through the trouble of finding those two. All right. Okay, then from here, I'm not going to do all the plug-in, but just I want to make sure that we get this integral done correctly. All right, when we do something like this, remember, this one is easy, right? When we do sine of x, that's going to be negative cosine of x. All right, but here we have to be careful. All right, we have a composite function. All right, now when you have that, when we look at that 2x, remember, what is the derivative of 2x? It's 2. But I don't see a 2 out here, so I'm going to have to write 1/2. And then the integral of cosine is negative sine of 2x. Okay? All right, so again, right, watch out when we have a composite function. All right, I got to make sure, remember, you can always check your work by working backwards here. All right, so here, excuse me, that should be positive. The integral of cosine is a positive sign. All right, I had that backwards. Okay, so remember, you can always double check your work by taking the derivative of this, right? If you take the derivative of this, derivative of sine is cosine 2x. Chain rule says derivative of the inside is 2, so you multiply by 2 to get back a coefficient of 1. Okay? So be careful when we have those composite functions. So that'll be my integral, and again, I won't plug it in. I'm assuming that we can take it from there. So you'll get something like this, and then you'll plug in pi over 6 inside. All right? Now for the next one, you'll have, all right, the integral of sine of x is negative cosine x. Right? And again here, right, it's just, it's not a composite function, it's just x, so I don't need to divide by anything. And then out here we'll have 1/2 sine of 2x. And again, I won't plug it in. I'll let you guys can finish it off from here. Okay, so after you plug in both of those, you add the two values that result. Okay, any questions on this example here? Just 1/2. It should be positive. 3 pi over 2 is out of our domain, Grusam, right? If we look at the picture that was given to us, right? So here, so if we look at the picture that we had this was just looking at the paper here. This was so this was the shaded region that they gave me. It said find the area of the shaded region. Okay, well here this is pi over 2. Then pi was somewhere out here. 3 pi over 2 is somewhere out here. But again, like I said, it's out of the domain, right? So it's not part of where the shaded region is. If I wanted to keep going here, and let's say I wanted to figure out the next kind of loop where it kind of hits, then we will take into account 3 pi over 2. Okay, so that's why I disregard it, right? 3 pi over 2 bigger than pi, so we see it has to be somewhere out there. Okay? Does that make sense, Grusam? Okay, let's look at number 6 on the review. All right. Okay, so we got number 6 and then number 10 after that. Okay, so here's what we got. We have the integral of cosine of pi over x squared. Okay, and then, so again, we have another composite function. Now, a good way to always, to try something like this, just to get us started is, I'm going to let u equal to pi over x. All right. Now, the reason why is, again, I want to kind of make some kind of substitution so that my resulting integral is something that is straightforward. It's easy. It's a basic integral, right? Now, the reason that I kind of start to see why this has to be the substitution, if I think of what's the derivative of 1 over x, right? Again, right? Don't worry about the constant, right? Always worry about just the variable, right? The derivative of 1 over x is negative 1 over x squared. And I see the x squared out there. I don't see a negative or a pi, but again, don't worry about that, right? All we care about is the function of x. Okay, so now let's look at what would du give us. Du would be, remember, that's just a constant, so power rule is this, right? Again, that's just x to the negative 1. All right. Okay, and then here we'll put du over pi negative is equal to 1 over x squared dx. Okay, and again in this step I just moved over the pi to the other side of the equation and the negative. And the reason for that is because if I look at this, I see that sitting out here. All right, x squared and dx. All right, so now I can do my substitution, right? When I substitute, cosine of pi over x becomes cosine of u. I replace x squared and dx with this. Okay, and now notice that with those substitutions, I have something that is one of our basic integrals, right? The integral of cosine of u is sine of u. And again, don't forget the plus c. All right, and then the last step is let me back substitute my u, right? Negative 1 pi sine of pi over x plus c. All right. Any questions on that example? All right, let's take a look at number 10 then. Okay, so for number 10, they give me an integral function. Okay, so here we have okay, and I would like to find a prime of x. Okay, now when we have something like this, keep in mind that t is just a dummy variable, right? Our variable is x. So if I have something, let me use a different variable here. Okay, so if I have something like this, right, again, t is our dummy variable, right? So what we have when we take the derivative of this, h prime of x, what we'll get is simply just f of x. Okay? All right, and this is from the first part of the fundamental theorem of calculus. All right, so now here I have to remember that in order for me to apply this part of the theorem is it has to look like this. Okay, so what I'm gonna do here, my a of x needs some work here. Okay, so what I'll do here is we'll go, all right, this goes from x to a. Okay. All right, and again, almost there. I have to make sure to make it look like this. Let me flip these around, but again, if you flip them around, make sure you write a negative there. Right, those are one of the properties of our antiderivative. Okay, all right, now I'm ready to take the derivative. All right. Okay, so from here, I'm going to take the derivative of this. The first one is easy. This one is just an x. So when I find a prime of x, again, just take that x and plug it in for the t, our dummy variable. Okay, now the next one is a little bit tricky. We have to remember that this is not just x, it's a function of x, so we're going to use our chain rule. Right? The chain rule is the first part, applying the rule. Okay? Right, applying the rule as is, but again, taking the chain rule, the derivative of sine of x is cosine of x. So we'll get that. All right. Okay, any questions on this example here? Maybe, yeah. I would definitely can ask you something like this. Yes, this is the answer, right? We're taking a derivative, so this is our derivative of our integral function. No, the chain rule comes here, right? When we take the derivative of a function like this, it just says take this and plug it in for t. Right? But then after that, the chain rule, remember what the chain rule states, right? The chain rule when we have the chain rule, right, just very generally it looks something like this, and then almost like layers, right? It says take the derivative of the outer function, you'll leave the inner function alone as is, and then you have to multiply by the derivative of the inner function. Okay, so when we do something like this, right, we see, okay, so taking the derivative of my outer function here, right, that means just plug that in there, right? Plug the sine of x wherever we see a t. So that's the first part, right? I've taken the derivative of the outer function. Okay, so then I'll go to the next step is now take the derivative of the inner function, and the inner function is sine of x. All right, so I'll take the derivative of that. All right, and derivative of sine of x is cosine of x, and that's where that one came from. Okay. All right, so let's see. Let's look at, let's see, we'll do 11. 11 and then 13. Yeah, if it was x squared, then you would multiply by 2x, right? The derivative of x squared. Okay, so we want to use the general slicing method. So here we want the area from -1 to 1 of a of x dx, where the slice is going to be okay, so the slice here is of length y, and it's going to be a square. Because of the equation. Right? So this is the equation of a half circle, and this is telling me the radius, so it's a radius 1. Okay, so keep in mind that this is the general form of our equation of a circle. If we solve for y, we get something like this. Okay, and since we're in the upper half, we chose the positive one. Okay, and just looking at what they give us, right, given information, it's 1 minus x squared, so that is telling me that the radius is 1, right? If there was a 4 there, that would tell me that the value here would have to be 2, right? Because then the radius would be 2, right? 2 squared gives you that 4 there. Okay? All right. Okay, so if we're all clear, I'm going to move on here. So now let's look at the slice that we're going to take, right? We're going to make a square out of this, right? So the further along we're on here, the closer we are to the edge, the smaller the square. The further as we get to the middle, we get bigger squares, then it starts to get smaller and smaller. All right, so each slice, the figure that is getting made is something like this, right? Now, if you have the review in front of you, there's a much better picture there that is in at least kind of 3D. Okay? Okay, so then from there, the area of my square is going to be y squared, right? Side times side. Okay, so now I'm going to plug in the value for y, right? Y is equal to the square root of 1 minus x squared, so we'll go from negative 1 to 1 of 1 minus x squared dx. Okay. So again, no more root because we're just taking the y squared. So that'll eliminate the root. Okay, so now another thing that I notice here is that this is an even function. And I have a symmetric interval, which means I can do that. I can go twice from 0 to 1. Okay, and then here what I'll get is twice. That would be 0 to 1. It's a polynomial, so we'll just get 1 minus 1/3. And then that gives me 4/3. Okay. Okay, and that would be the volume of that solid. Okay, any questions? Okay, so let's see. We wanted to look. That was 11. So let's do number 13 then. Yes, it does. But then I just plug in 1, right? and then it goes back to being 1. Right, again, remember the intervals from 0 to 1, and when I have a polynomial, right, I just integrate it, so this is x, but you're just going to plug in 1, so you get 1. And this is 1/3 x cubed, but you plug in 1, so you're left with 1/3. All right, it's all good. Okay, so now let's take a look at number 13. Okay, so for number 13, we have y is equal to sine of x, y is equal to cosine of x. All right. Okay, so let's see here, and then they tell us that x is between pi over 4 and 0. All right. Okay, so let's draw a little picture here. So we're gonna draw here sine of x looks something like this, and then cosine of x, this is 1, looks something like this. All right, just more or less, right? Rough sketch, and then here is where they meet. All right, and that's at pi over 4, right? That's when the sine and the cosine are equal to each other, right? And again, that's for my unit circle. All right, that's not the best drawing, but you get the idea here. All right, so we want to take this region here, and I want to rotate it about the x-axis. All right, so again, I'm going to use, it's going to be a dx. And it looks something like this. Okay, so we're going to have a, not a this method, but a washer, right? We're going to have, this part is going to be empty. The solid is going to be between these two curves here. So when I go around there, it'll look something like that. Okay. So again, we're going to use our formula here where we're going to have all right, it'll be pi times the radius squared. Now this is for the this method. All right. All right, when we have a washer, it'll be pi r outer squared minus pi r inner squared. And in this case, we're dealing with dx. Okay, so what we'll have here is my integral is going to run from 0 to pi over 4, where they intersect. And I'm going to factor out the pi from both of them, right? I'm going to take the pi out here. And the radius of the outer one squared is cosine squared x minus the inner one, sine squared x. All right, and that'll be times dx. Okay, any questions so far? Okay, so let's see here. All right, excuse me. Okay, so from here, what I have is, well, I need to integrate this. I know how to integrate cosine squared. Correct, it is the outermost, the top function, so it's always r squared outer minus r squared inner. Okay, just think of what we're finding, right? If you think of when we have something like this, right? If you look at the slice, right, what we're going to have is we want to find the area of the solid part, though, that's trapped in between the two curves, right? So it'll always be the outer one, right, the top curve, minus the inner one, the inner curve. Okay? Okay. All right, so now from here it's a matter of, all right, how do I integrate this, right? Now keep in mind this is not a, you have cosine squared sine squared, and it's a minus, right? So I need, actually, looking at this, I'm going to need an identity. I don't know how to integrate this just as it stands, the cosine squared x and the sine squared x. All right, so I'm going to need an identity, and actually, as it turns out, here, let's see here. All right. Okay, so I'm going to need an identity here, so I look at here what I have, and again, I didn't put it on here, but I will provide you with any identities that you might need. I would expect you to know the Pythagorean identity ones, but something like this where it's a double angle, I'll give you the double angle identities. Okay, so now from here, we have cosine of 2x all right, and now that becomes, again, a much more straightforward integral. Okay, always remember here, be careful here. So when I take the integral of this, it'll be sine of 2x, but again, don't forget that 2, I gotta make sure to compensate it out here, right? Derivative of that is just 2, it's not out here, so make sure you divide by that constant and evaluate it at pi over 4 and 0. Okay. Again, you guys can plug it in from there. Um, let's see, what else do we need? Number 8? All right, let's look at number 8 if there's no questions on this example. Okay, so for number 8, no, the Riemann sum formulas, I'll provide those as well if we're going to calculate our Riemann sum. Okay, so for number 8, one thing I do notice here for B, there's a bit of a typo there. Says find velocity. B should say find the position. Okay. So when we started going over derivatives, we had a position function, right? So if we had S of t then we were able to find the velocity function v of t by taking the derivative of the position function. All right, and then we were able to find the acceleration by taking the derivative of the velocity function, or s double prime of t. So what we're doing here now is we're essentially working backwards in a sense, right? If we're given a of t, then what is going to happen here is if I have a derivative by taking an antiderivative, I'm able to find the velocity function. Okay, and essentially what I get here is that's by taking the derivative of both sides of, or excuse me, the antiderivative of both sides of this equation. Right? This here, again, their antiderivative of derivative is just that function v of t. Right? Which means that to come up with v of t, we need to find the antiderivative of sine of pi t over 4 dt. Okay. Okay, then from here, we'll take the antiderivative. So v of t, antiderivative of sine is going to be negative cosine. Okay, now here we have to be careful. Again, I don't want to ignore what's inside here, right? If we remember, again, a composition here, the derivative of this is just going to be pi over 4, right, if our variable is t. But if pi over 4 is not on here, just make sure to multiply by the reciprocal there. So I'm going to multiply by 4 over pi. And again, this is a definite integral, so make sure you write plus c. All right, I'm going to clean this up a little bit, and I'm going to have negative 8 pi cosine of pi t over 4 plus c. Okay, now I'm still not done with the velocity because they give me a plus c here. So as of now, I have a family of functions, but I'm actually given more information, right? I'm actually given a way to find c, right? If you look at the initial velocity, is this, right? That was given information. Well, what would you like me to explain, Gursimrit? The minus, well, it's just positive 4 over pi, and that comes from this in here, right? The minus comes from the derivative of the antiderivative of sine. It's the negative cosine. That's where that comes here. All right. Again, if you're having trouble seeing this, I would do this. And then du is going to be pi over 4 dt. Okay, so that way now when you have this integral, what you'll have is you'll have twice. And if this is du, that means that 4 over pi du is equal to dt. So when you plug this, when you do the substitution, you'll get something like that. Okay, and now we see that's where the 4 over pi came in. All right, so from here, we're going to use the initial condition given to us. All right, so again, that is given. So we'll have v of 0 is equal to cosine. When we plug in 0 here, we get cosine of 0, which is 1. So we get negative 8 pi plus c equals to negative 8 over pi. And all this means is that c is equal to 0, right? Solving for c. All right, so now I have v of t I have that to be my velocity function. Okay, and now again to get the position function, all right, to get a position function, what we're going to have is we're going to work our way backwards again, right? If we have v of t to be equal to s prime of t, right, taking an antiderivative gives me s of t is equal to the antiderivative of v of t. All right, so which means that here, to get to my s of t, we'll have, I'll bring the constant out on the outside. Okay, and then I'll do my antiderivative again from here, right? Antiderivative of cosine is sine, but again, we're going to have the same thing here, right? If we do, we have to make sure to be careful here. So let's u be equal to pi over 4t, which means that du is going to be pi over 4 dt, or in other words, 4 over pi du is equal to dt. So when I substitute, we're going to get negative 8 over pi times another 4 over pi cosine of u d, which means we'll get negative 32 pi squared. And let me just take the antiderivative of this, right? Antiderivative of cosine is sine of u and then plus b. All right, but let me, I don't want u, I want t. Okay, and again, I'll use my given information. They tell me that s of 0 is equal to 0. So when I plug in 0 here, I get sine of 0, which is 0. So again, once again, c is equal to 0. So my position function is negative 32 pi squared sine of pi t over 4. Okay, any other questions? Maybe I have time for one more if you guys have it. If not, we can call it an evening. Okay. All right, sounds good. Then I'll see you guys tomorrow. Izmir, what would you like me to go over? I plug in my initial conditions. and solve for C. When you plug in 0 here, you get sine of 0, that's 0, and this whole thing has to equal to 0. So yeah, that's all I'm doing there. I'm just plugging in. Okay. Okay, number 9. So, okay, we'll wrap this up with doing number 9 here. Okay, so number 9. Okay, so number 9 we want to, well, first we want to look at what the region in the first quadrant looks like here. Okay. All right, so y equals to x cubed looks something like this. All right, now this other one, so it's a parabola pointed downwards, and it crosses the x-axis, doing some factoring here. So it crosses the x-axis at 0, and then at 2. So it looks something like this, more or less. All right, again, this is just a rough sketch. Where that'll be 2. Okay, so it looks something like this, and in fact, what I would like to know is where does it intersect? Right, because now if I'm looking at the region bounded by these two curves, then I'm looking for this region, right? R would be right here. All right, so it's in the first quadrant. I can find this by, let's set the curves. I can guess at it, but actually, let's set them equal to each other, see what we get. Okay, so again, I'm just looking for the values where they intersect. I got x equals 0, but I had got that one already from the graph. So here, going further here, let me factor this x. Okay, so the solution to this, x equals 0, x equals 1, x equals to negative 2. This is not in quadrant 1, so I'm not going to need it. All right, so the other one is this point here, 1. Okay, so how do I find the area? Top curve minus bottom curve. So the top curve is the parabola, and the bottom curve is the cubic function. All right, and here the limits of integration are going to go from 0 to 1, right, in the first quadrant. All right, and again from here, looking at this, this is from 0 to 1. It's a polynomial, so when I take the integral of this, all I really care about are the coefficients. So this will be 1, that'll be 1/3, and that'll be 1/4. And then you guys can wrap it up from there, right? You can combine those three numbers. Okay, Marlon, does that Marlon and Gershomrit, does this clear up number 9 for you guys? From 1 to 2, no. No, we only need the region in bounded by the two curves is only the region from 0 to 1. I would do, yes, it's always the top curve minus the bottom curve. Watch your parentheses in how you write something there. So if you have 3x plus 3, it's minus 2x plus 2. All right, you don't really need parentheses here, but make sure that it's parentheses, yes. Yes, that minus would be distributed. Okay, if you don't, then you'll get the incorrect answer. Okay, all right, so then why don't we wrap this up, and then I'll see you guys tomorrow. I don't remember off the top of my head, Gerson, right? More than one. Okay, all right. Thank you guys. I will see you guys tomorrow.